So last video we discussed momentum, impulse, force, time, change in momentum, and how those all relate. Now we're going to look at conservation of momentum and the law that encompasses that. So quickly, let's review Newton's laws. The third law says for every reaction force there's an equal and opposite reaction force. So two forces, one's positive, one's negative, but they are equal. Other than that, Newton's second law, acceleration is equal to force divided by mass, or F equals ma, as you call it, FMA, some of you do. So those are Newton's first and second laws. So let's talk about how this relates to collisions. Okay, we have a golf ball sitting still. We have a golf club moving in this direction, and it hits it. All right. So as it hits the ball, there's a little bit of recoil, and that's that leftward force that the club head gets. The golf ball experiences a rightward force. Right. We know both these forces are equal. Okay, they have the same magnitude, just in opposite direction. So the force that the ball puts on the golf club is equal to the one that the golf club puts on the ball. Another example is billiards. Here we have a 7 ball hitting an 8 ball, right? So the 7 ball hits the 8 ball. The 8 ball puts a force back on the 7 ball while also getting a force from the 7. And these are equal forces. They just go in opposite directions. So our net force is going to be 0 in the whole scheme of things. Now, law of momentum conservation. So for a collision between two objects in an isolated system, and we'll talk about isolated system here in a little bit, the total momentum of the two objects before the collision is equal to the total momentum of the two objects after the collision. So any momentum lost by object 1 is gained by object 2. So you'll see this written like you have two objects with momentum, right? They can have separate velocities or the same, doesn't matter. But their mass times their velocity is their momentum. You add the two objects together, that's your initial momentum, if you will. That's initial. Then you have your final velocities after they collide, which they could change velocities. I'll call this V3 and this V4. But at the end of the day, their momentums added together, you start with is equal what you end with. That's conservation. But essentially, if one loses momentum, two will gain it. It's a net sum. It's a zero sum answer. So here's the logic behind this law. First off, third law, the forces are equal and opposite in directions. They are in contact for the exact same time. Now, we know impulse is force times time. So the impulses are equal in magnitude and opposite in directions. Now, if that's true, then the change in momentum on each side of the equal sign has to be equal and opposite in direction, because impulse equals change in momentum. So we start with the third law. We throw time into the equation, time of contact, and all of a sudden we got impulse and change in momentum. So we have proven the law of conservation of momentum from what we talked about in the previous video. So let's take an example, and this is a pretty simple example. We got a car driving with a mass on it. Another mass is dropped on top of it to increase the mass of the cart. Okay, so this is before the collision and after the collision. Now, I call this a momentum grid, and this is how I do momentum problems. And what I do is I have the initial, or before, and the final, or after. And I'm just giving them random numbers. So initially, the cart's moving, and let's say it has a momentum of 45, mass times velocity. The brick is just sitting there and has no momentum. If I add those two together, my momentum I start with is 45 total. Now, if momentum is conserved, my momentum final, momentum initial will always be the same. There'll be no change. So now I got to find my final momentum. Well, let's say once I drop the brick on it, right, and the car slows down, which it should, the momentum of the brick is 14 and of the cart is 31. Now, I don't necessarily know the one of the cart, but I know that when I drop the 14 on there, it's a change. So if it gains 14, then the cart will have to lose 14 because momentum is conserved. So we have to make that assumption that whatever one gains, the other loses. So our net change will be 0. We also know that our momentum at the beginning total will equal the momentum at the end because of conservation. So a couple of examples with not a lot of numbers. You have a fullback carrying the football with 100 kilograms meters per second momentum, and a linebacker that's traveling 120 kilograms meters per second. And when this collision occurs, the linebacker and fullback come together, right? Their masses join, but the linebacker applies a so we get the linebacker will apply the net momentum, which will be 20 going to the left, and we would call that to the left would be negative. Negative 20 kilograms per meter per second, or kilograms times meters per second. And that's what we would get. So momentum before equals momentum after. 100 plus negative 120 equals negative 20. And that's the momentum we have after. We got a clown standing still, so that means no momentum. And we're throwing a medicine ball at the clown with a momentum of 80. After the clown catches it, the clown and the medicine ball will have a momentum of 80. Again, 80 plus 0 equals 80. Total momentum before equals total momentum after. Now, what is an isolated system? An isolated system is when there's no friction. Okay, the only unbalanced forces occur from within the system. So it's going to be applied force, normal force, gravity, the things that deal with the two objects that are colliding. There is no friction. Okay, and we know that's impossible in real life, but in an isolated system, we're talking about no friction. So here's an example. We have the medicine ball being thrown with a velocity of 20 kilometers per hour to a 60 kilogram person who is at rest on ice. The person catches the ball and then slides with the ball across the ice. We want to find how fast the person will be moving after the collision. This is the type of problem that conservation of momentum helps us with. Because I know the momentum of the ball, and if I add that to the momentum of the ice skater, it will equal the momentum of the ball and ice skater after. Okay, that's what we expect to see. So here's how we solve that. Is we make a chart. The person has no momentum before the collision. The medicine ball's momentum, 15 times 20, which is 300. Now, I kept my units kilograms times kilometers per hour. As long as my units are consistent, I don't have to change to meters per second in momentum problems. So that's a welcome change from what we did with the kinematics. So when I add those two together, 0 plus 300, I know that my total is 300 kilograms times kilometers per hour, which means my after collision momentum is also 300. Now I don't know the velocities, so I take the mass of the person, 60 times v, plus the mass of the medicine ball, 15 times v, and make it equal to 300. So I make a nice little equation here, solving for v. I combine like terms, divide by 75, and I get a velocity of 4 kilometers per hour. So the ice skater and the ball are both traveling to the right, because it's positive, 4 kilometers per hour. Another example, we got a baseball catcher catching the ball. So we have a mass of the baseball. We have the speed of the baseball in meters per second. It strikes the catcher's glove that's at rest with this mass. The mitt recoils backwards before the catcher stops its momentum, right before he puts his impulse on it. If the catcher's hand is in a relaxed state at the time of the collision, it can be assumed there is no external forces existing. So it's going to hit the mitt, and the mitt's going to go backwards. We want to find the post-collision velocity of both the mitt and the ball. Again, the momentum before will equal the momentum after. I make a chart. Before the collision, I take mass times velocity of the ball. The mitt's standing still. Add those together, and that's my initial momentum, 6.75. I know my final momentum is the same as my initial. Then I just take the information I know after, which is just the mass of the ball times its velocity, and the mass of the mitt times its velocity, which are the same because they come together. I make an equation, combine like terms, divide, and the velocity of the mitt and ball as it goes backwards is 16.9 meters per second. We have two trucks. So we have a truck that's 3,000 kilograms, and it's moving with a velocity of 10 meters per second and hits a parked car. The car is set in motion 15 meters per second. Now, if we conserve momentum, and again, isolated system, no friction, what is the velocity of the truck right after the collision? That's what we're going to try to find, the velocity of the truck right after the collision. So that's what we're looking for here. Again, momentum before equals momentum after. I make a chart and fill out what I can. The truck's mass times velocity gives me 30,000. The car standing still at 0. 30,000 plus 0 is 30,000. After the collision, the truck, I don't know. So it's 3,000 times whatever velocity. But the car is traveling positive to the right, so it's positive. So I take 1,000 times 15, and I get 15,000. So I know the momentum of the car, but not the truck. But I know if I add those two together, it's going to equal 30,000, where I get this equation. So I bring the 15,000 over, divide by 3,000, and I get a final velocity of 5 meters per second for the truck. So the truck's still going to the right, but a lot slower because it applied an impulse to the car. Again, no friction here. So examples of using the equation. How about you have two people in space. One's in motion, one's at rest. When the person in motion hits the person at rest, they will go in motion together at the same speed. So I can say mv plus mv, if this collision is where they stick together, equals 2 mv. M before times velocity before equals m after times velocity after. So if we have a small fish and a big fish, again, if in motion at 2 meters per second, if the fish is 3 and this fish is 1, if the big fish eats the small fish, their total mass is 4. The velocity is going to have to decrease. Let's look at before. We got a train backing up into an at-rest caboose, and as it backs up, we got 20 here and 0 here, right? 20m and 0. But when they come together, it makes 6m equal to 20m, so it's going to be, a velocity will be less when they're combined than it was for the red one before. And again, it's because my mass increased. Explosions. Momentum conservation in explosions. A firecracker explodes. All the parts of the firecracker shoot off in opposite directions. But the sum of all their momentums will still equal 0 because the firecracker had 0 before the explosion. Before the explosion, after the explosion. Again, no momentum before the explosion, but if it shoots out the ball, this will go backwards. But their momentum together, one's positive, one's negative, will equal 0. Before explosion, after explosion, again, total momentum equals 0. Why? Because this is negative 20 and that's positive 20. Positive 20 plus negative 20 equals 0. Equal and opposite momentum changes. So before the explosion, they're at 0. After the explosion, look at the velocities and masses multiplying by each other. They should be exactly the same when we talk about momentum, just one's negative. Here, 20, here 20, but this one's negative. Here, this is negative 20, this is positive 20, and you can see the theme. If the object is if the objects are before the explosion, when they go away, their momentums are going to be equal and opposite, very similar to what we see in Newton's third law. Here's an example. We got a tennis ball and a homemade cannon. The cannon is at rest when it is ignited. After the impulse, a photogate timer measures the recoil backwards at distance and time. First thing is we put all units in kilograms. So I take the tennis ball, put it in kilograms, and I find the velocity. But since it's going in the negative direction, it'll be negative 280 centimeters per second. Punch the numbers into my chart. No momentum before, which means no momentum after. Then I add them together, make them equal to 0. And I bring the 355 over, divide by this number here, and I get a velocity of 6323 centimeters per second. And that's going to be going in the positive direction. Hopefully this made sense. If you have any questions, please let me know.